Hello everyone and welcome to MES's e-learning channel. So in this video we'll try to understand the floating point number representation. So representing a normal number, a natural number is not a problem inside a computer. But if you have a floating point number, the decimal point which is there, after having such kind of a number, saving that kind of a number is a big problem. So how these kind of numbers are saved inside the computer, that's what we're trying to understand here. So basically there are two formats that we have. One is the IEEE 754 32-bit format, which is also called as the single precision format, and the other one is the IEEE 754 64-bit format, which is also called as a double precision format. So IEEE, everybody is aware what is IEEE. 754 is the release number of this thing that they have, and this is 32-bit, as in the number representation happens in 32 bits. Here 64 bits, meaning the number is represented in 64 bits as a whole. So let's try to first understand what is a floating point number. So we are all somewhat aware what a floating point number is. Still, I'll give you an idea what exactly it is. So here for our reference, I've written a number. So if you observe, there's a decimal point here, okay? So this decimal point makes this a number, a decimal point number or a floating point number. So this decimal point basically can float anywhere, hence it is called as a floating point number. One, it has a decimal point. Also the decimal point can float here and there, hence it is a floating point number. So here the number can have a decimal point, the number can be a positive number or a negative number, that has to be taken care of. So basically what is the number one step that is done is that the number is normalized. So what basically normalization means is that we fix the position of the decimal point so that the decimal point does not float here and there. And basically what is the idea behind doing that is, so for example, if you see, if I have this number 4 is 100, right? So this is 4, so saving number 4 is not difficult. But in case if you have 100.0, this is again a 4, but since there's a decimal point, this number has to be saved as 4.0, right? This is 4 and this is a 0. So that's a problem. So basically this thing, what basically we are trying to do is we are trying to normalize a number. So again, what I'm trying to tell you is that why normalization is important is that we have to fix the floating point. So basically if we have a number over here, so what normalization basically means is that we try to move the decimal point. So for example, if we have this number 10.01, so what normalization means is that we bring this decimal point at that position. What position? So wherever from the MSB side, we have to see which one do we have, the very first one that is there. After that, we put the decimal point. So what are we going to do? We are going to take this decimal point from here and we are going to place it here. So basically this is our MSB bit, and after the MSB bit, this is the first one which occurs, right? So we are going to move the decimal point over here. So if the decimal point shifts, so the number is going to become 01.010001. Now again we are shifting the point, so that has to be taken into consideration. So we'll have to write what do we do when we move a decimal point? We'll have to write 2 raised to something. Now what is that something? We've moved by 3 places. So what are we going to have? We are going to have 2 raised to 3. Now again, why are we writing 2 over here? So generally when we shift a point in normal numbers, decimal numbers, what do? We write into 10 raised to by whatever place we have shifted the number. So in decimal, the base of decimal numbers is 10. So we write 10. Now we are dealing with binary numbers. The base of binary numbers is 2. Hence 2 raised to whatever positioning you're doing, right? I hope that's clear. So if you're moving the decimal point, you obviously have to adjust it, right? So that's why we have written this into 2 raised to something, the places by which you have moved the decimal point. So this is the normalized form. So what is the idea of doing this is that the computer keeps in mind that yes, before the decimal point there is going to be 1, and after that the numbers can be whatever. So this thing is fixed, that there's going to be a 1 before the decimal point, right? Also there is going to be a 2 with some exponent factor. Again, one more thing which has to be taken into consideration is that if the number is a positive number or a negative number. Now, if you observe, the first number which I have written, which is nothing but this number, is a positive number. So this is a positive number, but then the second number which I have written here is a negative number. Now also that has to be saved. So how a negative sign is going to be saved inside a computer? There is no provision to save a negative sign. So how do we save this negative sign is that we'll have one more term over here. So what is that one more term going to be? We will have a -1, okay, and then we are going to have something over here. So we will either have a 0 or a 1. So if we have a negative number, here we'll have a 0 or a 1. What are we going to have? If we have a negative number, we'll have to write 1 over here, and if we have a positive number, we'll write 0 over here. So if this is 0, anything raised to 0 becomes 1, so automatically the entire number becomes positive. And if we write -1 raised to 1, automatically -1 raised to 1 makes this a -1 itself. So -1 into the entire number makes the number negative. So this is how the number is saved. So this is called as normalization of the number 1. What we did, we moved the decimal point after the very first one that had occurred in the number, and then by whatever numbers we have shifted the decimal point, that has been adjusted with 2 raised to some exponent, and then we also have a -1. So -1 raised to a 0 or a 1, this will take care of the sign of the number. So this is the normalization of the number in general. So if we write it in a generalized format, this is how it is. Can we say it? So we have a -1 which is fixed. Then we'll have a sign. This sign can either be a 0 or a 1 depending on what the number is. It's a positive number or a negative number. Then we have a 1 always before the decimal point. Whatever is after the decimal point is called as the mantissa. Okay, it is called as the mantissa, or let's simply represent it as m. So 1, always a 1, then a decimal point, it is fixed, right? We have designed it that way. And then we have all the numbers. These numbers are called as mantissa, multiplied with what? 2 and some exponent by what the decimal point has been shifted. So this is the generalized pattern of the number, right? This is the normalized pattern. So this is what is there. So now what is IEEE 754 32-bit format? So if you see, in the 32-bit format, the total if you see, this numbers which I have written inside is the number of bits, okay? So the sign bit is 1 bit, this is 8 bits, mantissa is of 23 bits. So now obviously we know sign as in what? This -1 is fixed, so we don't have to save that. We'll either have to write a 0 or a 1 to tell if the number is positive or negative. If the number is positive, we simply write 0, right? So automatically this becomes 1. Anything raised to 0 is a 1. So -1 raised to 0 is also 1, right? So we'll either write a 0 or a 1. So only one single bit is required to do that. Then we have this mantissa. So mantissa is only this part after the decimal point. So we take this mantissa and we put it over here. So there are total of 23 bits assigned. So we can represent that in 23 bits. And then finally we also have what? We have this exponent. So obviously everything is going to be raised to 2 only. So we have 2. So we don't have to save 2. What are we going to save? We are only going to save this number which we have as an exponent. So to save the exponent, we have a total of 8 bits. So what is 8 bits? If there are 8 bits, then the number can be of how many? What can be the number? It can be what? 2 raised to 8. So what can the number be? 2 raised to 8 is what? Nothing but 256. So again, bias exponent can be what? It can be positive or it can be negative, right? So that has to be taken care of. So that is why there is something called as a bias value which has to be added with the exponent, right? So bias value is what? In this case, it is 127. So now from where this 127 has come, let's try to understand. So since there are 8 bits, I told you since it is 8, 2 raised to 8 is what? 256. So 256, so if this is 256, if we divide it is what? 128, right? If we divide it by 2 in equal parts, we have a total of 128. So we can have 128 positive numbers and 128 negative numbers, right? Fair enough. But we also have a 0. So we have 128 on the negative side till 0 till 128. Right, but if you make a total of this doesn't make 256, it makes a 250, what? 257. So that is why what we do is, instead of keeping it as 128, the bias value, we have kept it as 127, right? So everything gets accommodated. So we have what? We get the negative numbers also, we get all the positive numbers, only one bit gets wasted, so that's not a problem. But basically what we do, we add a bias value of 127 to whatever is the exponent, and while extracting back the number, simply the bias value has to be removed. So that is the care which is taken to save a negative exponent. Here we had a positive exponent, so there's not a problem. But if we have a negative exponent, that has to be taken care of. So that is why we have to add a bias value. Again, why the bias value is 127? Because here we have 8 bits to represent the exponent, and 8 means 2 raised to 8. We have a total of 256 numbers. So half of 256 is 128. But if we take 128, it's creating a problem on the negative side. Hence, what we have done, we have taken one bit less and 127. Okay, I hope this is clear. So now let's see for the 64-bit format. Again, for the sign bit, we only have one single bit. Then for the bias exponent, 11 bits. And the mantissa is of 52 bits. Now, again, since we have 11 bits, 2 raised to 11 is 2048. And the half of it, since we have to represent both positive as well as negative, since the exponent can be a positive or a negative number, so the range starts from what? If it is 2048, we can have 1024 negative numbers and 1024 positive numbers. So again, there's a 0 in the middle as well. So instead of taking the exact half, we take 1 less. So 1 less, that is why we will have 1023 as our bias value, which we will add with the exponent which we have. For example, if we have 3 as the exponent over here, so we will add 3 with the bias value. It has to be added. So we'll add it with 1023. So 3 plus 1023 is going to be 1026. And then whatever is the binary equivalent of that number is going to be placed over here. And the mantissa is nothing but this part. So we'll place it over here in the mantissa section. Okay. So that's all. So in 32-bit format, if you see, the total of these bits makes the addition of 32, and this makes an addition of 64 bits. So this is how floating point numbers are represented inside a computer. I hope you've understood. We'll take an example of both the formats for easy understanding. If you have any doubt, you can put them down in the comment section below. Thank you for watching.